Welcome to Chemistry Connections. Our names are
Max Warias
and Harris Hamid, and we are your hosts for episode 8 called Chemistry of Apollo 11. Today we will be discussing the chemistry of the history of the Apollo 11 mission.
So, this all starts back in the 1960s. The U.S. was going through a Cold War between the U.S. and Russia, and we were in a technological race to see who could get what technology first, and this was especially space-focused. Russia had a lot of firsts in the space scene. They sent up the first person into space, as well as the first satellite and the first dog. But
sadly, the dog did not come back.
The dog did not come back.
Sad.
Yes,
so
they sent up a second dog with the same name actually, but that one also did not come back.
So to the U.S., this was embarrassing. They're in a Cold War at the moment, and they're losing technologically. So to the U.S. economy, they're behind and they're losing. Yeah. So it's kind of a double hit for them. So they wanted something to get ahead and get an edge on Russia, so they're more technologically advanced.
So at a university speech that he was giving, Kennedy issued a challenge. He said that there should be a man on the moon from the U.S. Within the next few years. And this set off a massive space race, or a massive next part of the space race with Russia, where both countries were rushing to send people into space as quickly as possible and try to establish space dominance over the other country. And the pinnacle of this was sending a man to the moon and having him come back safely.
With that type of advancement, you would instantly prove that you are the better country when it comes to technological advancements.
Yeah.
For sure.
It was something that people had been dreaming of for thousands of years, but of course nobody had ever done it, so it was a big thing. Yeah.
So this mission, I'm pretty sure Kennedy said he wanted it done within a decade, and it took the U.S. 8 years to succeed in this endeavor. And the mission was called, obviously, the Apollo 11 mission. Now, I'm going to just briefly go over just what the mission was and how the U.S. went about it. So the main part they used you had to get to the moon. So the first half of the mission was getting out of Earth's atmosphere. You had to get out of Earth and then get en route to the moon. So the first part they used was the Saturn V rocket. This rocket was like 360 feet tall. It was massive. It had 3 different stages in order to get the rocket out of Earth, and each one had its own part, and then after in space, each part would start to break off.
May I note, this was entirely hand machined by people on physical machines. There was no computer machining or anything like this at the time. There were physical people saying, I'm going to go machine a rocket engine for 3 months for a rocket. And there are still 3 Saturn Vs in existence to this day, all hand machined.
There's also one in a museum that's literally hanging on the ceiling, which is pretty cool.
Pretty dope.
Hanging from the ceiling.
I've seen that one and another one.
I am jealous. That was cool.
They're super cool.
So the first stage had 5 F-1 rocket engines, and they lasted for around 2 minutes 40 seconds and put the rocket around 42 miles in the air. Then that half broke off. Then the stage 2 was used, which was powered by 5 J2 rockets, a little less powerful, but they lasted a little bit longer for 9 minutes 12 seconds and went an extra 109 miles up. Now, stage 3 is what's going to be used for the majority of the rest of the mission. And that's what's going to get them to the moon and back. This was powered by 1 J2 rocket, and it got them 118 miles up, which was known as the parking orbit, and it took it around 12 minutes. Now, the parking orbit was an important part of the mission. It's where they were out of Earth's atmosphere, so they weren't being attracted back down to Earth's, by gravity. They're just rotating around the Earth. So this is where they can do their systems check and make sure everything's working properly while they're just slowly rotating around the Earth.
Think of it as a good stopping point. If they need to take an extra couple of rotations around the Earth, as long as they know where they are, they're perfectly safe to stay there for pretty much as long as they want, as long as they don't run out of stuff. There was nothing slowing them down, so they're just kind of whipping around the planet until they decide to accelerate off towards the moon.
I believe they did this for around 2 hours, just to ensure everything was fine. And then the main 3 parts that were used to get to the moon were the Lunar Command and Service modules. Lunar module is what landed on the moon. The service module contained the electrical components and was used to enter and exit lunar orbit. And the command module is where the astronauts spent basically all their time when they weren't on the moon. It's where they had their controls and where they sat during their mission. Oh, fun fact, didn't mention this. I found out this while researching about this. The tip of the Saturn V had an escape, not hatch, but escape
Oh,
system.
yeah.
It was like a little rod. If you look at a Saturn V, you look at the tip of it, it has like a long, pointy rod. That was a backup in case the rockets blew up at the bottom. That would shoot out and just take the command module and fly straight in the air away from the explosion.
Yeah, actually, it wouldn't fly it straight in the air. They
Straight?
had gyroscopic acceleration, so it would spin and then careen off to one side based
That's
on
cool.
little adjustments in the little gyroscopic engines that would take them away from the thing that was exploding instead of just straight up into the air.
So that was a nice backup that they thankfully did not need,
They
but
did
that's
not need.
really smart.
They needed it beforehand on previous ones, so they made sure they had it for this one.
So getting to the Earth, they had to do something really cool. The command and service module had to do like a 180 and dock with itself because the lunar module was inside of the entire rocket. So they had to disconnect, do a 180 turn, get the rocket or get the lunar module, and then back out again.
Yeah.
So that was really cool. And then that's what they used. So once they got to the moon, they did a few orbits to make sure everything was fine. And then they started their process for landing. So there was a descent and ascent stage, so descending and ascending from the moon, or going down to the moon
Yeah.
and getting back up from the moon.
Think of the thing that stayed in space as kind of like the home base, and the lunar module just took the people down and then took them back up and redocked and put the people back on the command module, which was still orbiting the moon. So the main command module never actually touched the moon, only the lunar module did.
Feel bad for that one person who had to stay in that module and couldn't go to the
Yeah.
moon because he had to be in orbit to make sure. Because once the lunar module touched down, they had only a few minutes to properly touch down, or else they would have run out of fuel. So that had to be quick. So once they walked around, said their famous quotes, left their footprints, left the American flag, and left. This was, I think, one of the most important parts of the mission was guiding the lunar so that it would connect back with the service module properly.
Yeah.
So they had to watch the rotation of it around the moon and then angle themselves so they can connect at the right moment, or else they would miss. And at that point, if they missed, they wouldn't have enough fuel to reconnect.
Yeah.
So that was really important that they reconnected. But once they did, which they did correctly because this was a very, very meticulously calculated mission. Once they got that, they went back towards Earth, and that's when the second challenge came, which was landing back on Earth. But the chemistry behind the rockets is pretty interesting as well, because you have 3 different stages with 3 different rockets, and they're all lasting for different amounts of time and being used for different amounts of time. So that's pretty interesting as well, how that works.
As far as the chemistry behind the actual rocket propulsion, rocket propulsion consists of 2 main parts, right? So there's the fuel, which is typically a hydrocarbon like kerosene or benzene or something like that, and then an oxidizing agent, either oxygen or something that has a lot of oxygen in it that will release it during the reaction. This typically produces CO2 and H2O, carbon dioxide and water, as exhaust, which is then shot out the back of the rocket to propel the rocket. And because these reactions are super, super high energy, so they release a lot of heat, which is what propels the gases out, is it expands against it and pressures it out. So the first stage used kerosene and oxygen in a pretty standard hydrocarbon combustion reaction, producing carbon dioxide and water. Kerosene is a mix of a bunch of different hydrocarbons in a kind of standardized formula, but it was just hydrocarbons that it reacted. The second stage, the second and third stage actually, used hydrogen and oxygen gas, which was also a combustion reaction, but it produced only water and no carbon dioxide. But once they were in space, obviously they needed to have some way to orient themselves rotationally. So they had these little thrusters on the side of the spaceship that would shoot in different directions and allow the spaceship to spin around in space controllably. And those used a pseudo-combustion reaction between monomethyl hydrogen as the fuel and dinitrogen tetroxide as oxidizer. So the monomethyl hydrogen had a lot of nitrogen and hydrogen, and the nitrogen tetroxide had a lot of oxygen, so those would react. But that created nitrogen gas carbon dioxide and water instead of just carbon dioxide and water. So
Stage 1 was also the most powerful, just to get that big ton of rocket up and far enough. And then stage 1 and 2 were the most powerful, because that's what was needed to get out of Earth. So
yeah, get out of the orbit. But then the third stage was mostly used for establishing orbit and stuff like that, which is, needs to be high efficiency, but not necessarily super high power. So the general idea behind the propulsion is the manipulation of gases, which typically behave according to this equation: PV equals nRT. Pressure times volume equals quantity of gas times temperature times the ideal gas constant. So this is called the ideal gas law. And rocket scientists figured out when they were developing rockets that engines are at peak efficiency when the exhaust plume is straight, or the exhaust that is coming out of the back of the rocket has an equal pressure with the surrounding air, so it doesn't get compressed inwards and it doesn't expand outwards. So to do this, rocket scientists developed rocket nozzles to gradually increase the volume, to decrease the pressure until it matches the surrounding air, and also cools down the gas to maximize the output velocity. So with these two things in mind, the rocket scientists managed to develop each of these stages with those things in mind. And of course, that was all to get there. But of course, getting back.
Yeah, so once we were able to slingshot ourselves back en route to Earth, Earth has this interesting... The moon didn't have this issue of re-entry. Re-entry is something that they had to make sure they understood. When you're re-entering Earth's atmosphere, it burns whatever's coming in. You basically turn into a meteorite.
Yeah, think about shooting stars across the sky. That's giant rocks basically skipping across Earth's atmosphere, creating massive fireballs from the ionization of the gases from the extreme heat that's generated, right? So that's what causes all of that to happen. And obviously this was a problem for the command module on the way down.
Because incoming objects are moving at high speeds. So as they are moving, they compress the air in front of them, and according to the gas laws mentioned earlier by Max, compressing a gas heats it up, and there's a whole lot of compressing going on during re-entry, so it just turns into that fireball Max mentioned. So the command module needed a material, obviously, to survive this fireball re-entry, or else our astronauts would have been cooked alive before they even hit or splashed down in the Atlantic Ocean, or was it the Pacific? Before they splashed down.
Before they splashed down in the ocean.
So
it was just south. I believe it was the Atlantic Ocean.
There was also a interesting fact. There was a military aircraft carrier waiting for them to get a helicopter and get them to safety.
Yeah.
So when I found this out, I thought it was amazing. So enthalpy is, you know what enthalpy is the is like a measurement of energy in a thermodynamic system, like the change in heat, right? So enthalpy of melting was taking place here. So we needed a substance that could withstand the heat, and that was really hard because with re-entry, it's so hot. What is it, 3,000 degrees Celsius? That would melt any metal that they tried using. So they use a specific resin called phenolic formaldehyde resin. So basically, when it entered Earth's atmosphere, the re-entry and all this heat would melt away the resin, and that resin would absorb all the heat. So all that energy that would melt the command module just melted the resin that was used as the heat shield.
Yeah, and then the resin would drip off in a liquid state after absorbing all that heat and also absorbing the enthalpy of melting to take off as much energy as possible.
So all that energy is just gone. It's just using the resin, and then it just melts away. So the command module doesn't have to face all that intense heat and energy, so it doesn't burn up. Because the specific heat capacity is 0.92 kilojoules per kilogram K. That was for the resin. So because of that, it was able to just char off the sides.
Yeah, and note that is an extremely high specific heat, right? Or specific heat capacity. Water is considered extremely high, and it's 1. So having a solid that has a specific heat capacity of 0.92 means that it could absorb a massive amount of energy without increasing in temperature very much.
So that was used as a heat shield. It also had a few coverings such as a pore seal, moisture barrier, just a little, just to make it waterproof when they crashed out.
Yeah.
So now that they have survived re-entry because of their use of enthalpy and ensuring that it chars off, doesn't melt the command module, it's now entering Earth's atmosphere, no longer on a fireball, but there's still, it's like skydiving, you're still crashing down. Even if they hit the water full force, that still would be very dangerous. So after that, they had really big parachutes that deployed, like 3 big parachutes would just deploy out of the command module and slow down their descent straight into the ocean. And that's where I said earlier there was an aircraft carrier waiting for them. So at that point, we just completed 8 years worth of engineering and design and a mission of getting to the moon, getting someone on the moon, and then coming back safe and sound. This entire massive Saturn V rocket, like this thing was like 363 feet tall. Imagine a big water bottle, right? And then the command module is just the cap.
Yeah.
That's all that's left.
From seeing the rocket in person, especially I got to get really up close and personal with it in Houston, Texas. They have it lying on its side. It takes like 3 or 4 minutes to run down the length of it. I did it. It's big. Your brain doesn't really fully understand how large it is, and then you look at everything, and every single piece of the rocket is so meticulously designed. It is all hand machined. Again, it blows my mind. I don't even know how you would even go about starting to do something like that.
That big as well. Even with today's technology that takes so much time, and this was done back in the 60s. Like, come on. That's insane.
Nowadays, they 3D print rockets, and it takes years.
Yeah.
And they did this back in the 60s with hand machining, machinists writing down notes about what tolerances they needed to have for certain parts and stuff like that. It's really fantastic. In fact, because all of those notes have been lost, they can't make Saturn Vs anymore. The machinist notes have been lost, so they don't know how to make every single part anymore. So they would have to go through a massive amount of redesign and rethinking in order to make another Saturn V, which makes it so unique.
Like nowadays, we have machines. Most machines you see in any machine shop, whether it be a robotic shop or a manufacturing company, you just type something on a computer, it does it for you. Everything's autonomized. But back then, none of that existed. Yeah. You had hands and tools.
CNCs wouldn't come around until about 10 years later. CNCs, computer numerical control machines, wouldn't come around until about 10 years later, and they wouldn't be available to any real extent or be useful to any real extent until long after that. So it's really just amazing how the power of human ingenuity allowed them to do something like this in completely handmade, hand-drawn everything.
I feel like just by us geeking out over this, you can tell we've both had a personal stake with engineering. We've had some experience with it. I think that's one of the main reasons I was so blown away and wanted to do this topic, because during the 20th century, having someone go to the moon and come back was huge. Even today, if we were to send someone to the moon and come back, I'm thinking that's insane, because you don't think about it. You can look outside and see the moon. You're like, oh, that's pretty close. That thing is far away. And having enough fuel to get there and then get back and then survive re-entry is a massive thing. And having done an engineering design process and gone through and looking through computer science and learning languages and seeing how everything works, it's complex stuff. It ain't easy. And I've made a rocket in aerospace engineering, just a basic little thing. And even that took weeks of me trying to figure every meticulous thing out just for the rocket to fly straight up for like 10 seconds.
Yeah, they had board meetings of the best minds in the world working on this issue, and they were successful.
Technically, really it's only U.S. because Russia, they got that tension, who can get there first. This just proved to Russia, hey, we did it. We're cool. We're better than you. We're technologically advanced. This was great for the U.S. It's such a, an ego booster for the U.S.
Yeah, big ego booster for the U.S. Put us at the top pretty much until now.
It really reveals the advancements made with technology and how far and wide we can really reach. I feel like most people look at a smartphone, they have no idea how it works. It's just a piece of glass that does everything you want. But when you dive in, there's so much we can do with what we have access to, and it's absolutely mind-blowing.
Okay.
All right, so thank you for listening to this episode of Chemistry Connections. For more student-ran podcasts and digital content, please make sure you visit www.hvspn.com. Thank you.